Welcome to the session. I am Bhagya Lakshmi, Associate Professor, Department of Civil Engineering, Satyabama University. I am going to handle the session on groundwater hydrology. Before going to the session in detail, I want to start the session with an introduction about water resources. In the entire global water content, 97.5% of water is in ocean as saline water, only 2.5% as fresh water. In the 2.5% of fresh water content, more than 60% is in glaciers, not able to use in any usable purpose. The 30% is groundwater, only 0.4% is as surface and atmospheric water. As per the data collected from the Ministry of Water Resources, Government of India, the total available replenishable groundwater resources for the country is estimated as 433 billion cubic meter. Out of this 433 billion cubic meter, 34 billion cubic meter as natural outflow. The net available groundwater is estimated as 399 billion cubic meter. In 399 billion cubic meter, only 231 billion cubic meter as for groundwater withdrawal. In the 231 billion cubic meter, 213 billion cubic meter for irrigation purpose, only 18 billion cubic meter for domestic purposes. In the groundwater balance, so to maintain the sustainability, we need to maintain the balance between groundwater recharge and discharge. So, consider the aquifer as a basin. So, water enters into the aquifer through the process of recharge, water leaves from the aquifer through the process of discharge. So, general recharge components are, apart from the rainfall, the recharge components, return flow from the irrigation field, the seepage from the nearby basins, from the nearby rivers, streams considered as recharge components. So, discharge components are evapotranspiration and then outflow from the basin, and then withdrawal is considered as the general discharge component. While coming to the groundwater balance equation, the left hand side is summation of recharge component, the right hand side is summation of discharge component with changes in storage. So, delta S is considered as changes in storage. To find out the changes in storage, we can find out, first find out summation of recharge component, then minus summation of discharge components. Next we come to the hydrogeological formation. Hydrogeological formation is nothing but under the ground, the geological formation that can able to hold the water and transmit the water. First one is aquifer. Aquifer is very good hydrogeological formation. The saturated and permeable in nature, it can able to hold the water and transmit the water in appreciable amount. So, in this figure, the brown color indicate the confining unit, see above which the unconfined aquifer, below the confining unit, which is called as confined aquifer. Confined aquifer is nothing but confined with the impermeable stratum. Water is under pressure. The pressure may be greater than atmospheric pressure. Above the confining unit is called as unconfined aquifer. See, unconfined aquifer is nothing but the top water surface contact with atmosphere. So, water is in atmospheric nature. Next one is aquiclude. Aquiclude is nothing but saturated geological unit. It can also able to hold the water from, but transmittance capacity is very less. Next one is acutard. Acutard also can able to hold the water and it can be able to transmit the water. When compared to aquifer, acutard transmittance capacity is very low. Next is aquifuge. Aquifuge neither contains nor transmit any water. We can say solid impermeable. So, for example, granite is an example for aquifuge. Next one, perched water under the ground. Impermeable stratum can able to hold the water, that is known as perched water table. Next one is, in this figure, in unconfined aquifer, the red color circle indicates the groundwater flow from the unconfined aquifer to the river. So, this river or stream is known as gaining stream. Why it is called as gaining stream? From the aquifer, water is entering to the river. Some stream is known as losing stream. Losing stream is nothing but from the river, water is reached to aquifer. Below is confined aquifer is there, below which in confined aquifer, the upper layer is acutard. Acutard is generally called as leaky aquifer. Through its pores, the water reached to this confined aquifer flow. The next one is Darcy's law. To explain the groundwater flow, we need to discuss with the Darcy's law. The Darcy's law, the engineer Darcy explained the relationship between the seepage velocity or flow velocity with the hydraulic gradient. Flow velocity is directly proportional to the hydraulic gradient. V is proportional to I. I is nothing but the ratio between the head loss, the difference in head level piezometric head H1 minus H2 divided by length of flow. While coming to the rate of flow, Q equal to K into A into I. K is the hydraulic conductivity or constant of proportionality or coefficient of permeability. A is the area of the aquifer. I is the hydraulic gradient. So next one is aquifer parameters. Here we need to compare with hydraulic conductivity and permeability. Both the parameter discuss the ability of transmittance from one point to other point. Here permeability is nothing but it deals about the property of medium, it does not depend the property of fluid. Whereas hydraulic conductivity, it also explains the capacity or ability to transmit the water from one point to other point, but hydraulic conductivity depends the property of medium as well as property of fluid. For example, the fluid density, fluid viscosity, then fluid quality, everything depends. While we are talking about hydraulic conductivity. Next we can compare hydraulic conductivity with the transmissibility. Hydraulic conductivity explains the transmittance capacity of the medium. Transmissibility also explains the rate of flow, but it considers the depth of aquifer. So transmissibility is nothing but rate of flow under unit hydraulic gradient under unit width of aquifer. In this diagram, the square indicates the square explains the hydraulic conductivity, this rectangle explains the transmissibility. This square explains the rate of flow per unit hydraulic gradient per unit cross sectional area. This rectangle explains the rate of flow per unit area per unit hydraulic gradient per unit width of the aquifer. So we can say T equal to K into B. K is nothing but hydraulic conductivity, B is nothing but width of the aquifer. This figure explains the hydraulic conductivity in three-dimensional way, Kx, Ky and Kz. The next one, we can write the equation Q equal to K into I into A. K is nothing but hydraulic conductivity, I is nothing but hydraulic gradient. Hydraulic gradient is nothing but difference between the head loss and the length of flow. And then area is nothing but the product of width of the aquifer and depth of the aquifer. The equation may be Q equal to K into I into A. Next we can rewrite the equation K into I into A is nothing but W into B. While we are talking about transmissibility, transmissibility is nothing but rate of flow per unit hydraulic gradient per unit area per unit width of the aquifer. So here width of the aquifer B equal to 1. So the equation maybe we can rewrite Qx equal to minus B Kxx into dou phi by dou x minus Bk xy into dou phi by dou y. So dou phi by dou x and dou phi by dou y is known as hydraulic gradient component in xx direction and xy direction. So generally B into K referred as transmissibility. Already we explained what is transmissibility. Transmissibility is nothing but rate of flow per unit hydraulic gradient per unit width of aquifer. So T equal to K into B. So the equation may be Qx equal to minus Txx dou phi by dou x minus Txy dou phi by dou y. Next component is storativity. Storativity is nothing but volume of water retained or volume of water retained or yielded from the aquifer per unit changes in the head component. So till now we have discussed about the aquifer parameters, hydraulic conductivity, permeability, transmissibility, storativity. So in next session we can discuss about groundwater flow equations for both confined aquifer and unconfined aquifer. Thank you.